And just a reminder to everyone also that we will be recording this. So I'm going to go ahead and start recording now, and this will be added to our website shortly after the event closes. So Eric, you want to go ahead and make some introductions. I think it's safe to go ahead and get started.
Absolutely. First of all, I want to thank everyone for attending today's workshop from the Agricultural Genome to Phenome Initiative. Just for those that may be new to this, this initiative is funded by the U.S. Department of Agriculture to create a shared vision across crop and livestock communities. This is one of a series of activities that the AG2Pi initiative does. We have a series of seminars, field days, and other activities to really bring together diverse communities in crop, agriculture, computer science, engineering, and anything to help prepare research for the future of agriculture. And so today is our workshop where we're going to have three presenters, Dr. Li Tang, Dr. Jinyao Gao, and Laurent Zhang. All of them are from Iowa State University in the Department of Agriculture and Biosystems Engineering, and they're also members of a unique institute there called the Plant Sciences Institute that really brings together these communities to address current and future challenges in agriculture. Today's workshop is going to be focused on enabling robotic systems for plant phenotyping, and with that, it is my great pleasure to turn this over to that team and look forward to your presentation today. Thank you all very much.
I'm going to share my screen. And to help with the streaming, I'm going to turn off my camera. Maybe I turn it on first and I turn it off later. And okay. Well, you see my PowerPoint?
Yes.
Okay. So yeah, thanks for the opportunity. So today, together with my former grad student, Dr. Jinyao Gai, and also my current PhD student, Liron Xiang, we're going to bring together a presentation. It's more like a workshop, and presentation. So it's kind of really a combination of some of the kind of review or summary about what we have been doing in my research group in the area of robotics automation for plant phenotyping. And after my my presentation, Liron Xiang would take over first to talk about how we can develop a deep learning algorithm for image processing. And then we're going to play the video, pre-recorded video of Dr. Jinyao Gai because he's now in China. The time difference won't allow him to really join this online lively. So Jinyao will be talking about a pipeline or process of how we can develop navigation control algorithms for the field robots. So that's basically what we are set out to do today. So whenever there's a chance for me to talk about robots, it's really exciting. I'm just really very passionate about this topic. And there are a lot of things we would like to share with you. Particularly in the recent years, my group has been really active in this very specific area called high throughput plant phenotyping. So we're going to share with you quite some videos and pictures. So to start with, I'm also going to start with a video clip, which is a clip from a video of a movie I really enjoyed watching when I was a kid. I don't know. I think some of you probably watched this in your early time. This is a video from Charlie Chaplin. About modern time. that crazy? So when I was a kid, I was really, really amazed by the performance of this actor. And we, in school, we start to mimic the way he walks, the way he whip his arms, and then everything. It was so funny. The memory was so deep in my mind. But when I grew up, I started realizing more about what really the actor was trying to tell us, right? He was trying to show us the drudgery, the hot life on the factory floor at that time. And given the context, this has connection to the first we call the first industrial revolution of humankind. Now we have moved into into the fourth generation of industrial revolution, and we are seeing the dawn of the fifth generation of the industrial revolution. And what we see now on the factory floor is more like this. This is a video I always show to my class in my automation system class I teach in the department. And you see here, you don't see people anymore. You don't see, Charlie is waving arms and then tightening the screws with wrench. Everything is done so beautifully and nicely by robots, right? And if we go back, look at the video I just played, you also probably would wonder, apart from the drudgery the actor tried to show us, we also would question where is the quality control at that time when people are so stretched to do this type of work, and do they apply enough torque to each screw there? So there certainly there's a question about the quality of the work as well. But if you look at this setting, wow, everything is so ensured, right? And we understand robot can really repeat the repetitive type of work in a very precise and accurate fashion. And so apart from the throughput in this type of robotic system, we also are, on the other hand, also are ensured by the quality of the work. And we trust the product coming out from this production line way, way more than what you saw from Charlie's movie. So come to our topic today about robotic phenotyping. So where are we now, and then what we are expecting to see to happen, and so what's the future in this area? And first, we need to look at in terms of the automation and the robotics in general in agricultural setting, and there are some unique challenges we are facing. Primarily because the objects we're working with, they are biological, so they have a lot of variables. There are variables in morphology, in how they are, planted, they are growing in the field, and all the environmental conditions like wind, the lighting, would add to the complexity of the environments we are working with. And so when we talk about robot is cool, right? But to have a really cool robot, it takes a lot of work and innovation. And this is the slide I would like to show people when I talk about agricultural robot, especially the mobile robot, which navigate by itself in the field. And there are multiple layers of technical components we have to work out, starting from the very bottom of the machine architecture in terms of hardware and software. And then we move on to the localization, perception, the navigation control, implement control, and then at the very top, you have intelligence in terms of mission planning and supervision. And all those layers, they require a lot of work in engineering to make them really work as together as a solid piece of equipment. So what I want to do again, give you heads up here is we are going to see a lot of new promises with the advancements in the technologies, and particularly in both hardware and software. And now we have a much more powerful computing technology. We have very advanced GPU technology that actually works hand in hand with our very amazing deep learning algorithms we are talking about everywhere nowadays. And so through the projects I'm going to present today, that's really what I want to show your audience. Yeah, there are a lot of new promises because the advancements in technology. So for my presentation, I basically going to kind of cover two categories of phenotyping robots. One category is the indoor phenotyping robot, and then we move on to the in-field phenotyping robots. For the indoor phenotyping, so mostly most of us, we know there are these something we call conveyance systems in the greenhouse where plants are conveyed to we call it screening stations, where you have different sensors to capture the information of the plant. So this type of system is we can find them in many places in the world. One of the most representative system is called the robotic system, but for when we move to the field-based phenotyping, it has been a very active research and development area in the recent years. We have seen a lot of new developments. As you can see in this slide, I put out some pictures from the internet, and that really shows different approaches and different concepts of field-based plant phenotyping robots, particularly the dramatic difference in the platforms. And we have more conventional high clearance tractor based than some of the more dedicated type of field robot based. And then we have more intimidating or more powerful gantry type of system, which can carry a lot of more advanced sensor suite. And we also have UAV, drones that can, take pictures in air and have very high throughput to cover large area. And it's difficult to really kind of put them in comparison because each system or each concept, they come with their different original pursuit. And depends on what the customer or developer they are really focusing on, then they come up with different design strategies. You can have bigger or smaller, taller or shorter, different type of platforms, and they all would come with their strengths, but also in the meantime some of the weaknesses as well. So when we talk about field-based phenotyping, I think there's an array of we call criteria that we are really considering when we start to work as an engineer, for example, start to work a system, a robotic system for the phenotyping in the field. And as a customer or a user, when you come to embrace the technology or considering adapting a technology, those are the things you also need to consider as well. For example, the autonomy, right? Whether the robot can go by itself, and is it safe to go by itself? And then the accuracy, how accurate the robot would be able to deliver in terms of the data quality, right? And then throughput, and is it faster than a human being, or is that meeting your expectation in terms of how fast it should work? And when we talk about high throughput nowadays, everybody is using that term, but we need to understand high throughput is really a relative term. It's it's relative to the expectation of whoever is talking about this, right? Then the mobility is very critical as well. Whether you can bring the robot to the sites or different places you would like to deploy, and how easy to transport, or how well the robot can interact with the working conditions like different soil surfaces. And then crops. Would this robot be able to work with tall growing crops? For example, the robot my group has been working on, which is primarily for tall growing crops like maize and sorghum. And so that's something you or as a user need to bear in mind to really think about would that robot really meet your expectation and fit into your application, and of course the cost would really fit into your budget. And so those things are really mutually important for any potential customer as well as for engineers when we set out to develop a system. So I'm going to start with the indoor system we have been working with, and then move on to the field-based phenotyping robot. So this system called Envirotron, and maybe some of you have already heard about this from different presentations from the team, the Envirotron team. So this is the project sponsored by the National Science Foundation under the Major Research Instrumentation Program. The idea is to come up with phenotyping facility. It's an indoor, which is drastically different than the current conveyor belt based system. So our idea was to really move the sensors to the plant instead of move the plant to the sensors. And so this is our pilot system so we create this facility. As you can see here, there are 8 growth chambers, and then there is a mobile agent called we call it Envirotron rover. So that rover would basically navigate into different growth chambers, and of course there is a suite of sensors that are installed on the robot arm, and then basically the mobile agent would be the carrier that would bring the sensors into different growth chambers, and also to interface with the plants in a very sensible way or intelligent way. So it won't have a collision. For example, when it's working in a growth chamber, in the meantime, it should be able to determine where and how to approach plant in the best way, based on different sensor, for example, sensor specifications. And we work with a local growth chamber manufacturer called Percival, and so we customized the growth chamber so that it would have room for the robot to come in and also to stay there while interacting with interfacing with the plants. So there is a sliding door, and then also there is a rolling curtain. So once the robot is in we call it vestibule area, the curtain will be rolled up, and then the robot arm would come in to take the images and probe the plants and collecting data automatically. The strength of the Envirotron is in control of different environmental variables. And we understand if you have a growth chamber, there are many variables in terms of environment you can manipulate. So we can control the temperature, daylight length, and the light intensity, humidity, CO2, soil moisture. My group, we spent quite a bit of time to try to come up with a good assembly of so many sensors we want to put together. One most important criteria is to really maximize their overlap so that we can cross-register the data from different sensors. As you can see here, we first did a very careful design in SolidWorks. So then we projected different view area of different sensors and try to maximize their overlap. And as you can also see from this slide, the sensors we integrate into the Envirotron rover is quite impressive. And we have from 2D, 3D, and imager sensors, and then thermal and hyperspectral. And we also have very high accuracy laser profilometer for 3D scanning. And on top of that, we have a probe that would allow us to, use the fluorometer probe to acquire the photosynthesis data from the leaf surface. The probing is technically is the most challenging part of this robotic operation. So that's something I want to share a bit more about how we approach that that task. This shows our current configuration of the rover, and this one, the video I'm playing here, shows the deployment of the probe. So in this chain that we call energy chain, there is a fiber optical probe, and to really ensure there is no sharp bending of the cable, so we have to use this kind of flexible chain to maintain minimum. So the minimum bending radius would not be going beyond the specification. So this is the video we collected recently to show the workflow of the environmental rover. So it leaves the docking station, the charging station, and we are using local map of the facility. So you see there is no magnet tape anymore as what we used in the very beginning. So it's navigating by using pre-generated virtual map. Well, the last part shows the leaf probing. So as you can see, the environmental rover is equipped with multiple sensor heads, and so one of the major strengths this rover can provide is the multi-model of the sensor data, and also the cross-registration of different sensor data. So you would have we call a holistic presentation of the plant from different sensors in terms of color, temperature, and then different reflectancy at different wavelengths. And we also have we call web interface for the planning of the experiment. So as a user, you can use the app to define your experiment chamber by chamber in terms of the lighting, temperature, humidity ordering, and the CO2. So you can specify the profile of those variables along the time, how you would like to change them through your experiment. And then your design will be saved and then uploaded to the server. And then the rover and the chambers, they are all linked to the server to take over from there to run the experiment fully autonomously. And next, I want to kind of introduce you. I call it a sibling system Envirotron. It's more narrowly focused to drought research. So this is a collaboration with colleague Dr. Yang Hai Yin at Iowa State University. This is also sponsored by Plant Sciences Institute at Iowa State. So what we are trying to accomplish here is to come up with unique equipment that would help with the drought research. The plant we are using here is this model plant, Arabidopsis. And so the whole design concept is to, similar to our environmental rover, so we would have multiple sensors including actuators for ordering on the robot arm. And the robot arm also is on a mobile platform, so it can really be its usage can be maximized if you have multiple, we call it climate rooms where the robot is working in. So it can travel into different rooms to maximize its usage. And the workflow is really to first place the parts on the table, and then in the meantime memorize their location, and then based on your prescription of different moisture levels for each part, the robot would determine how much water to add into each part based on that prescription. In the meantime, when the watering is done, then we also take pictures at each time. And the picture is not just 2D image. We also incorporate the 3D scanning from multiple angles. So then we can reconstruct very high fidelity, high resolution 3D image. I call it holographic image of the plant. So this video shows the operation of the road system. So the road system has been in operation for about 2 years now, and it really has been tested, and it has generated a lot of data, high quality data for the drought research. And one of the really strong aspects of this system is not just only the autonomy, also the super 3D traits. And I think it's the only system we are aware of that can produce this holographic type of 3D image, which allows the scientists to extract very detailed morphological traits of this model plant. So now I'm going to move on to kind of talk about our work for the field-based phenotyping. Primarily, I'm going to talk about our phenobot development, and also along with that, the sensor, we customized the 3D sensor called phenostereo. So phenobot project also is sponsored by National Science Foundation under the Major Research and Implementation Program. And we have been really working on this for more than 5 years now. To start with, this project representation, I actually recently I participated in the PSI, Plant Science Institute workshop we have here on campus, and so my colleague Sotiris, he presented his crop modeling research. So I captured the list he used in terms of the traits he collected in the field for the corn plants. So on this list, he put together 7 different traits he collected in order to run his crop model. And so if we go to that list, I'm trying to kind of see which traits that can be possibly measured by the phenobot, and which traits which are probably maybe in the future we can do something about it, or some of the traits which we cannot really do well in the field, and or the traits which we probably have to do it by hand. So after starting this list, I start to group them into different categories. One is, so those traits, for example, silken date, and this is a silken interval maturity date, and then leaf number and leaf area, fraction light interception. I think those traits can be possibly measured by robot in the field through field-based imaging. And then the traits regarding kernels, can be done by imaging, but it has to be done after harvesting in the lab. Then he also measured some of the chemical concentration, like nitrogen, carbon, and nitrogen uptake. I think there can be a potential to do that in the field if we incorporate, some of the more innovative biosensors, like some of the work my colleague Liang Dong is doing. Then if we deploy that type of sensor by using field robots, so there is a possibility we can do that also in the field. Then regarding the plant biomass, so biomass is a difficult, trait to collect. Then we have to collect the plants and then bring into the lab and then dry it and weigh it. So I wonder, is there any kind of proxy substitute that can tell the same parameter like plant biomass by using, for example, stalk size plus the plant height plus leaf area, and those things we can, likely we can measure them in the field through some of the research and development. But whether that's something can be done or should be done is still a question that we need to pursue the answer. So with all those things in the background, when we start to work on this project, and we had a very strong ambition, we want to do a lot of things. We want to create a robot that would be able to accomplish a lot. And actually, before we start this phenobot project, we already had a couple, other projects before that, and that's something we kind of really named them as phenobot 1. We started work on that by using a tractor platform. That project started in 2012, so that's quite some years ago. And then we move on to our second platform called phenobot 2, which we purchased a vehicle called Husky, and that's 2014. And then starting from 2016, we start to brainstorm our own version of the phenobot. So that's called the pre-version of our phenobot 3. And so since 2017, we have been really heavily engaged in the design and the development and testing of the phenobot 3. So in terms of phenobot 3, our thoughts are really linked to what do we want the robot to do, and also what are the constraints we are facing in the field. So the features I list on this slide really tell our thought process. And for example, the narrow row spacing, we have to accommodate 30-inch row spacing for corn plants. And then how to have a vehicle that would be more energy efficient, smoother to run in the field, and then also to be able to accommodate different heights of the plants. We are talking about corn and sorghum, and we understand they can grow pretty tall, and how we can collect traits at the upper level of canopy. So that would really require a pretty tall mast, or we call it sensor mast, so we can mount our cameras to image the plants at higher positions. And also for example, the power rating, right? How much power we need to put on board, and so the robot can run a number of hours in the field. And also, we don't want the robot to be too heavy, and that's not only for mobility, but also considering some soil compaction issues we may have if we run back and forth many times in the field on the same path. And also the sensor, given the very tight space we are giving here between the rows, whatever sensor we put in there would really have a very narrow field of view, because the sensing distance is very limited. So we have to really use multiple tiers of sensors or cameras to cover the entire plant. So having all those design expectations and also the constraints, and we really put together a lot of ideas to come up with something we call the better design robot that would be able to accomplish those measurements as you see on the screen. We are really focusing on the organ level traits, like look at the, for example, ears, tassels, leaves, stalks, and so we don't think that right now there is such a robot that can measure those traits properly in the field. So this slide shows when we design the robots, we kind of think about at different heights, what are the traits we should consider to collect. The sensor mast turned out to be probably the most challenging part of the whole design. And because we want to have a lot of functions on this mast, apart from multiple tiers of the cameras, also how we can balance this mast. Because once it's so tall, you can understand, especially our vehicle has to go between the rows, and which means it's going to be quite narrow. Our vehicle is only 20-inch wide, so it can subject to quite a lot of rolling because the uneven soil surface we are working with in the field. So any small rolling would be amplified with the tall mast, right? At the top of the mast, you would have a very dramatic motion. And so how can we really enable this robot to be able to even just be able to place the camera properly between the rows? And that's really a very stiff challenge through our entire development and design process. So we, in the beginning, we made our robot, our sensor mast retractable, which it can telescope and retract for different, when it's working with different heights of the plants. In terms of the mechanical design, the chassis, the powertrain is the most critical part of the vehicle, of the design. So what we end up with is to use to really integrate the differential gears for both the front and the rear drive assembly, power assembly. As you can tell here, this is really more like if you think about Tesla, and Tesla has two motors for their more higher end models, or together with the differential gears and the motor, you would be able to really produce the drive. And the differential gear is just so critical in terms of what kind of mechanical advantage it can offer to our vehicles. And so we customize our differential gearbox so it can fit into this very small small platform. So with the differential gears, the turning will be really smooth, and you don't see the problem commonly you find from those vehicles with a skid steer. And we also use this concept called central pivoting. Think about the very narrow passage we have in the field. We would like to have our vehicle to be more nimble, so it's more like as a more flexible body, so it can weave through or mingle through the narrow space between the roads. So there are two primary development tasks. One is the navigation. Once we have the robot developed, one is the navigation control. Another part is the imaging and the trait extraction. So I want to play this video to show you the video we took last year when we were testing the phenotyping in the field. Also, you see the cameras are there taking images, and the lights are the strobe lighting from the camera modules, which I'm going to introduce later in the presentation. And once you can realize, or when you watch this video, is the vibration we still have at the sensor mask. So after we tried our robot last summer, we realized we need to have a better design of the sensor mask, especially in terms of how we can balance it better in the field. So Dr. Jin Guy would present a tutorial about how he developed the navigation controllers for our Phenobot. And so basically, we believe there should be multiple approaches to ensure proper navigation of such kind of robot in the field. So we not only GPS-based navigation, we also looked into vision-based navigation for under canopy path tracking, also above the canopy proper road tracking. So I would leave this to Dr. Gag to introduce to you at the later part of this workshop. And again, this shows the overall layout of our navigation control system. And as you can tell here, we are utilizing multiple sensors, front mount 3D camera, and then GPS, IMU encoder. All those sensors, they are used to help with the navigation. And so Jin also created this simulation, very nice and useful simulation environment when he was developing the navigation controllers. So he would show you more details about how he created such kind of system and how it was so helpful for him to test and investigate different navigation strategies. So this picture shows, again, Jin's work in terms of under canopy navigation, where we use a 3D camera to identify crop rows under the canopy. And then this one shows the approach of over canopy above the crop row navigation. The road detection approach we took was very different, or because what we did, we converted the image into the frequency domain, and then in the frequency domain, we take the whole image and then try to find the patterns of those rows in the frequency domain. And in this way, you are really taking the overall information of your image and then discover the row distribution in the image without processing the image locally trying to find the crop rows. So that really enhanced the robustness of the road detection algorithm. As I mentioned before, our initial design of the Philippa 3 has some issues, primarily because the sensor mask is very heavy, And one day, I think when we were driving the robot back to the shed, then there was quite a sizable rabbit hole by the field, and then accidentally the robot fall into that rabbit hole, and then actually it's tipped over. So we learned a lot through the test last year, and then that really pushed us to rethink about our design. And that's the time when we had to rescue our robot when it's failed in the field. This really shows the complexity of our original sensor mask, the balancing mechanism. There are just so many components, and it's getting, once it's done, it's really too heavy than what we would like to have. And very difficult to maintain if there is anything wrong inside of the assembly. So this year we totally redesigned our the central linkage of the phenobot. As you can see in this screenshot, the whole design is much more simplified, and we also, most importantly, we also lowered the pivoted position of this sensor mask. So the pivoting axis is now in the plane, more or less in the plane of the axis of the vehicle. And we also reduced some of the payload we put onto the mast, and we shipped some of the payloads to the rear of the vehicle, and then removed the telescoping function of the mast. So we had a test this summer and really to examine how better this new design is in terms of the sensor mask stability. So this is the video we recorded in the field, and if you look at the mask now, it's way more stable than our previous version. So this phenobot 4.0, that's what I would call now, is going to be pretty much our final design of this platform. And we used the phenobot to collect a lot of data this summer. And for example, this video shows we are using phenobot to collect the leaf angle data for over, I think, 900 lines of maize plants in the field. And this is still controlled by a person walking behind with a joystick. We are still finalizing our navigation controller, and once we change the design of this vehicle, there are some changes we have to make in our navigation controller. So that's that work ongoing right now. Even with walking behind approach, we were able to cover that kind of panel about more than 900 lines or plots in about 3 to 4 hours. So I'm going to move on to talk about the sensor. As you can tell, the traits we are trying to collect, they are mostly morphological traits, and in terms of like leaf angle, stalk size, and now we are working on like leaf area. So all those traits really require imaging, right? They require images, and also more than that, they require 3D images. If we don't have very good 3D images, we would not be able to extract accurate measurements of those traits. So we really spent a lot of time to try to come up with a good stereo module. Because any 3D camera you probably can buy off the shelf would not really work in our situation well. And there are really a number of stiff challenges in the field, as I mentioned before. The lighting variation, right? How we can really overcome the variable lighting in the field. And And also the very short sensing range we are facing there, given the 30-inch row spacing and plus the space you have to allocate it to the sensors and the vehicle, we are talking about maximum probably 20 inches distance between the camera and your plant. So come up with a customized 3D module is really indispensable for the success of this project. And this picture shows our first generation of phenostereo. So where you see we have 4 tiers of stereo cameras. This was still our, this is work we did last year. And so we still have our original sensor mask there. And so we collect the 3D images at 4 different heights, and then we kind of put them together. We call it cross registration. First, I would like to show you the difference between, like, for the consumer grade camera, for example, this is our Garmin camera, and also it has a high definition video. And then on the right is our phenostereo. The 2 cameras were taking images in the same field under the same lighting condition. So this is what normally we should expect from like a GoPro type of camera, like Garmin camera. And then on the right, you see that's the picture we were able to capture by using our customized phenostereo camera. Well, you may wonder why the key pictures, the video showed, or the pictures showed on the right, captured by phenostereo, looks like the background is so dark. Did we capture the images, after sunset? No, as I said, those pictures were captured at the same time. So the thing we did here is we customized this camera so that would allow us to use strobing light or flashlight that then enable us to use very high shutter speed. That would essentially blocking out the background, which is really ideal for our application because we are really trying to analyze the images in the front row, but not anything in the background, correct? And secondly, the image is much more crisp, as you can see and hear, than in comparison to the consumer grade type of camera. So this has a tremendous benefit to 3D reconstruction. When we do stereo matching, we understand the quality of the stereo matching is really depending on the texture in the images, right? The more crisp your images are, the better insurance of the 3D matching the accuracy. So once we have this phenostereo camera developed, then the first project we did was to try to measure the stalk size of the plants. So one thing I want to draw your attention here is to look at the resolution. That's one thing of the point cloud we generated by our phenostereo, and also the clarity, the cleanness of the 3D point cloud we were able to generate by not just only our stereo matching algorithm, but more because the image produced by our phenostereo. So with this kind of high quality of point cloud data, and so my grad student Li Rongxiang, she's going to present after me. She developed this pipeline to come up with the detection and also the measurement of the stalk diameter of sorghum and corn plant. We call it stalk net. So this pipeline is already published. If you are interested, you can check out Li Rong's paper. What I really want to show you is the result we were able to obtain here. So we were able to really measure the stock diameter to the accuracy of like less than 2 millimeters. And the correlation between the caliper-based ground truthing and the image-based measurement is so strong. And we have the R value of 0.97. I think we are really pleased by what we were able to come up with with this stock net system. And then the next project Liron took on in connection with phenostereo is the leaf angle detection and characterization. What we are trying to do here is to use our phenobot, and we run the phenostereo cameras in the field, and we capture images at different heights by using our phenostereo cameras, and then try to come up with first the leaf angle detection algorithm, and then once the angle is detected, then we back project it into the 3D point cloud, and then at the end we measure the angle in 3-dimensional space. That would really allow us to overcome the issue of the different orientations of the leaf angle toward your imaging sensor. What you see here is the reconstructed the corn plant from 3 tiers of phenostereo cameras. Is this really lovely? Yeah, we are so pleased with what we will be able to produce in 3-dimensional space of the plants in such a quality. But identifying or detecting leaf angle is actually very difficult. At first, we were really doubting whether we can really do that. And so Liron she was able to be so creative to come up with a good algorithm through the deep learning approach to come up with first the detection algorithm by using key point detection approach. And so basically she specified 3 key points. One is on the leaf at the back of the leaf rib, and then one is at the collar, and then one is at the stem of the stalk. So with those 3 points and available or detected, then we can define the leaf angle in 3-dimensional space. So here I'm going to play a video clip Liron created that shows first on the left is the detection of the leaf angles. As you can see, it has a pretty high rate of detection. Of course, we would not be able to see all the leaf angles when they are not, presented properly to our camera. For example, it's totally occluded, or the leaves are basically kind of snapped. Some of them, like you can see in the picture. But other than that, the detection rate is really, really high. And on the right, you see the detection of the key points, which would give the definition of the leaf angle. So we then compared the results generated by this pipeline we called AngleNet, and with the ground truthing, and one is really by using protractor. Another one is you as a user to manually identify the key points and then define the leaf angle with the 3D image we reconstructed. And these are autonomously, detect the leaf angle. So this is the comparison, and we had a really strong correlation with the manually measured leaf angle in 3D point cloud. This is a little bit noisy here when we compare with the manual measurement by using the protractor. So what we think is when you are trying to measure this by hand in the field, there can be many variables when you place your protractor, against the plant, and you can easily have several degrees of variation when you do that, at multiple times. So this line shows some processor readout from different lines, E73 and MO17. As you can see, they have very distinctly different leaf angle distribution. This is more like sharp at the top and then gradually kind of flatten out at the bottom. And as you can see, what we were able to produce by our leaf angle angle-length pipeline. And this one shows the MO17. As you can tell here, is more like a parabola type of shape. And so that really validates our measurements. And this line shows the rate. In general, we can detect the angles of plants. As I mentioned, some leaf angles, when they are totally occluded or blocked from the camera, then we would not be able to see them. Otherwise, the algorithm is very strong in terms of detection of those angles at different heights. Then we move on to explore further. As I mentioned, about the list from the Sotiris, he has that list of 17 items in terms of traits he collected. And so the leaf area is very important trait for crop modeling, and is actually also one of the primary interests for many plant scientists to look at the leaf area, because it has direct connection to the photosynthesis activities. But to really be able to measure leaf area in such a tight space, it's very difficult. So this year we came up with a different version of the phenostereo, try to really lighten up the camera module. So we removed the case, which was there was an aluminum case of this phenostereo camera we made last year. So this year is a more like open structure. So we removed a lot of weight from the camera module. And then also we used more powerful strobe lighting modules to enhance the strength or intensity of the lighting. And what you see here is we, again, also have 4 tiers of cameras, but each tier we have a pair of phenostereos. So we are trying to expand the view of the phenostereo cameras at a different height, right? Then in the hope, we would like to capture in one single shot, we want to capture the more entirety of the plant. So then we can recover the leaf area in one single shot. So in the video, you probably don't see very clearly. We are strobing, or we are capturing 10 pictures per second when we are driving the phenobody in the field. And the shutter speed we are using is about 1/4000 second, which is really about 1/3 of millisecond. Some of the sample pictures we collected. And this shows the one example, 3D point clouds neuron generated by using our new phenostereo camera. So for leaf area measurements, we believe we also need to manipulate the view angle toward the leaf surface. So in this setup, as you can tell, we tilt our phenostereo cameras about 40 degrees downward. So in that way, we would have a better chance to see the top surface of the leaves. So these are some sample images we collected this summer. In this 3D point reconstruction. So this is something we are still working on, is to try to improve the cross-registration between multiple phenostereos. You know, our desire is to expand the horizontal view of the cameras. So at each single snapshot, we would be able to capture wider 3D point cloud data. So that way we can measure the leaf size more accurately. So this one shows the ongoing work we are doing in terms of the cross-registration of multiple phenostereo cameras. We are talking about cross-registering their point cloud, which is actually pretty difficult to do. Another project we are engaging right now by using the phenobot and the phenostereo is to characterize the seed pods of the soybean plants before harvest. Our approach is to use 3D imaging together with our phenobot to try to automatically detect the seed pods and also characterize them into different groups. For example, one-seeded pods, two-seeded, three-seeded, four-seeded, and also the length, width, and distribution of the pods on the plants. And so approach is to use the 3D imaging plus the machine learning image processing. So we just actually collect some deployed our phenobot and collect some data a couple of weeks ago. So we came up with this attachment, or we call it camera rig, to the phenobot, and then we can mount multiple phenostereo cameras to image the soybean plants from multiple angles, basically from two sides of the crop row. So we are working on the reconstruction and the processing algorithm right now. The last piece in my presentation, I think I've gone through 1 hour plus, is to really introduce you the product I developed. It's a very niche product called Plant Standard Analyzer. The idea is to come up with really, really high throughput, ground-based system that would be able to capture the distribution or distribution of the corn plants in the field. This has been a very long time project, and I started on this when I was a graduate student and really investigate the different approaches by using different type of sensors, starting from like a camcorder and then color camera and then 3D camera. So really developed several different types of systems for this application, but they all ended with a fundamental problem, which is inconvenient. As you can tell, the lighting can be a really challenging issue for all those camera-based approach, and also the amount of data the system needs to process, and it's tremendous. And also how fast we can really push this system in the field if we want to cover larger ground. And so there was some kind of frustration in this process. But there, one day, I think it's into the year 2006, I was in the field and looking at the corn plants and really think about, do I have to really use the cameras? And would there be other approach which is simpler that can really produce basically we want to detect corn plants, right? We want to get the counts of the corn plants. So if we sacrifice certain resolution and we use different sensors in terms of pictures, maybe we can do a better job. One thing I'm thinking about is to use the proximity sensor, which are commonly used in industrial automation, right? And we would have a better chance to use laser sensors, so that would have a better way to overcome the lighting variations in the field. So this slide really shows the journey of this development. As you can see, I have gone through many design concepts, and I want to show you some of them here in the slides I'm going to present. So this is a very early test of the concept in 2013. As you can see, I used a baby jogger, and I was testing that with my resident in Bao in the field. Well, as you can tell, it's a very kind of primitive design, but we would like to, at that time, come up with a kind of proof of concept, right? And we ended up with actually very encouraging results in terms of the accuracy. As you can see from here, our error ratio is really well below 3%, and most of the time we are running really right on. So we kind of brought our prototype and to different, seed companies and showed them the potential of this technology. For example, this one we did a demo in 2014 with the Syngenta installer in Iowa. And then once we have this proof of concept, then we start to try to motorize this application. And so this one shows our first attempt of motorizing the plant standard analyzer, right, called the PSA. But I made some mistakes during this development process, especially about the mechanical design, where the sensors should be placed, how should we design the whole toolbar, for example. And so I think every year I learned a lesson and then came back to how to design the system to overcome the issues we encounter in the field. One thing I realized is I used, in the beginning I was using a sled, more like a ski type thing. So, to glide on the surface of the soil surface. The dust was a really big problem. Then I in 2017, I moved to use wheels. And this one shows the actually 8-row version by using wheels. But I also made a mistake by putting this behind the vehicle. So dust can be a problem. Dust can be generated by the vehicle. Then immediately I start to move this whole thing into the front of the vehicle. And that's why you see the mirror design where I moved all the wheels in the front of the vehicle. And the wheels are really customized. It's more like the cooking pans we have at home. I asked the company to customize that so I can put my sensor inside of the wheel, the pans. So the concept really here is quite simplistic in terms of the sensing approach, where you see the dots are the data generated by the laser sensors. Then in my algorithm, I'm trying to delineate the data to find the linear structure of the stops. And so this one shows when the system is running in real time, that's what it's processing. And it can process the data in a very impressive speed. So last year we had our much better version, and as you can see in this video, where we can count arrows at a speed of more than 10 miles per hour. And this bottom screenshot, when the system is running, shows how the plants were detected in real time. So the driver or the operator would be able to spot any problems when the system is running in the field, because everything shows on the screen in real time. Sorry. So I don't know why this picture I lost. And to summarize this plant standard analyzer, it's a very, I think, classic example of how we push the technology toward one particular application, starting from the sensing approach to the design. And so I've gone through so many iterations to try to perfect this technology. And I think I'm right now on version of 11. Some of the characteristics of this PSA system is basically the high throughput, really the 10 miles per hour and 8 rows. And you can cover 1 acre in a mere of probably several minutes. And then it can be used for different platforms, tractors, UTV, and sprayer. Accuracy is very promising. It's constantly above 97% of the standard detection accuracy. Plus, it can also generate multiple metrics of the measurements, not only the population, but also the spacing between the stands and the gaps in the plots and the doubles, tillers, and also the estimation of the size of the stock. The data, once generated, can be automatically grouped into plots, so that then would be able to used by the researchers directly just after running the mapper program, like you see on the screen. So this mapper would process the stand count data and then first partition the data into plots automatically, and then also would allow the user to examine the results of the partitioning and also look at the distribution of the stands in different sections of your plots. And you can adjust or modify if any mistakes you identified in this partitioning process. What I want to really conclude or wrap up this presentation is with this example recently I found on the internet about the apple harvesting robot, and it's pretty impressive how this difficult task now is really very hopeful and promising. As you can see, how the throughput is pretty impressive. And but my question here is, not only look at the technology, but also look at the craft, how that worked together with the technology. So if our apple trays are like this, and as you can imagine, it would be much harder to deal with by any robot because the 3D structure of the canopy and then the blockage of the branches and leaves to the fruits, that would all bring a lot of difficulties to any automation approach for the apple harvesting. And so this robot works really well for this type of growing structure. We call it 2D trainer. So you basically train the apple trees to grow into kind of 2-dimensional plane. Then that would expose the fruits very well to the robot, and then in turn really facilitate the automation and the throughput of the robot. So my question here is, as a community, we have our own agendas, right? For research, as an engineer, I want to come up with the best technology that would help with, in this case, plant phenotyping. But on the other hand, as you can have observed through my presentation, there are some really difficult situations to come up with any sound solution, especially in the field. So is there any kind of room for us to really have a consolidation between the robotics engineers and also the plant scientists? I really think we will think about how we can really mutually facilitate each other. For example, is there any chance you can plant your crop with GPS equipment? So then that would allow the robot to be able to follow the planting path. So the path is there, right, already. And also, can we have a better way to control the roughness of the soil surface in the field? So then the robot would have better, stability when it's running in the field, and also weed control. And can we do diligent work to control weed? So then would have a better, would have a better way to save the plants in the field. And or more importantly, when it's possible, can we give more space for the robot to work with? I know, for the plant science research is now, we are now dealing with the production system. So we cannot really manipulate plants as what we could do like for those apple trees. But when there is a chance, for example, especially at the later growth stage, and when canopy is so thin, is it, for example, can we even just thin the plants so then we would clear up some space for the plant you are trying to image at the time of imaging. So those are things I would like to kind of bring out for us together to consider along with the robotic research and development work. So that kind of wrap up with my part, and I think I used quite a bit of time here. So I'm open for some questions. Nico, do I have time for questions?
Yeah, sure. If anyone has any, you can go ahead and unmute yourself and ask, or you can put them in the chat.
I have a question. So thank you for great presentation. It's really exciting. I'm also like engineering background, but my question is, in one of the slides you were showing like you measuring like a biomass using imaging. So I just want if you could a little bit give more information about that. How can we correlate like measuring like plant biomass through imaging?
Thank you. So I put a question mark there. Right now, yeah, we cannot really direct measure biomass by using imaging. But my question here is, can we come up with a proxy so then we can use, for example, the stalk size of the plant, and in addition to like the number of leaves or leaf area, those are main components that form the biomass of the plant. And those metrics, we have a chance, right, to measure them by using imaging. So can we use that to substitute the direct measurement of biomass?
Okay. Would you also consider like some sort of like combining with imaging and also some sort of like another sensing like non-destructive sensing that then probably measuring this whole biomass information? That I mean, it's very interesting and I think important for crop health. So that's why I'm very curious about it.
Well, I don't think we have a direct ways to measure the weight in the field. There might be, yeah, I think the biomass is a very difficult one to try to capture directly in the field without harvesting them. But I do have ideas or some motivations to do some work with some kind of physical operation, like with, for example, with a robot arm on board, and then we can do some physical manipulation of the plants. So then we can come up with different metrics of the measurements, or to deploy the sensors that would be able to come up with some chemical measurements, not just the image.
Thank you. One more question I have. It's recently I had a chance to talk to also Professor Hein Mercy, works on agriculture. So we were discussing about it, and he mentioned like one of the challenge for robotics is how to speed up, like let's say if you want to do food harvesting, the speed like of the harvesting time, how can we improve that? So if you could put some insight on that, like what like robotics should do to like speed up, like let's say because the farmers want to fruit be harvested like in a second or like 5 seconds per fruit, but still robot can't do that. So if you provide some insight on that, that would be great. Thank you.
Yeah, to increase the throughput. But if we talk about the phenotyping, I think it's a little bit different than production system. From the example I give for this robot harvesting, apple harvesting robot, and you can see the throughput is pretty impressive in my view. But it takes a special way of growing the plants now with the facility that automatic operation. As for plant phenotyping, we really have a lot of constraints. And if you want to come up with a way to capture data with good quality, more or less, you have to sacrifice one way or another certain throughput. And so it's always like a battle, or what kind of compromise you have to make from one end to another. And I learned a lot when I was working with the development of this my plant standard analyzer. And yeah, I had to work with my potential users and then understand what they really want. For example, the number one they want is the throughput, and because we are talking about 40, 50 acres per site, and they want to cover that, in just a matter of several hours. And yeah, try to come up with technology to really come up to have that throughput is their number one requirement. But there are some other situations like for a lot of professors in universities, they really want to see very detailed truths. Then some things like we are doing with the Phenobot would fit into that category much better. It has really detailed analysis or measurements of the traits.
All right, so we're getting a little short on time, and I want to make sure Laurent has enough time to at least get started in her tutorial. So if there are any remaining questions, can you please put them in chat, and Dr. Tang, perhaps you can answer them in chat, and then later I will put those into our one of our Slack channels, which I can share out later. So Laurent, do you want to go ahead and get started?
Yeah. Hi. Let me share my screen first. Okay. Hello everyone, I'm a PhD student in Dr. Tang's lab, and in this section we will discuss a convolutional neural network and work on a case study about beans classification. And as you can see here, we have 8 classes of different beans, and we will build a CNN model from scratch to classify those beans. Okay. Before I move to CNN, I want you take a look at this example picture. My question is, what you can see from this picture? Is it a man with bright face or a man who is looking at you directly? Feel free to speak out or put your answer in the chat box. Oh, both. I saw both. Well, okay, thank you for the reply. Actually, there's no right or wrong answer to this question. I would say if you are looking at the nose or the right contour, you probably saw a man with bright face. But if you are focusing on the ear and the left contour, you might see a man with front face. So the example here I want to show is when we are trying to interpret or classify an image, our brain is trying to capture some patterns like edges, contours, or some small objects like nose, ear. And we train our machine to detect such kind of patterns in a pretty similar way like us. CNN nowadays it has been popularly used in analyzing images in computer vision tasks. More generally, you can think of this a CNN model as an artificial neural network that is capable of detecting patterns in images. And this pattern detection function is what makes CNN so powerful and useful in image analysis. And as you can see in this picture, pointer. In this picture, the CNN model has some hidden layers, and each layer will get some input, transform the input in a certain way, and output that to the next layer. Here is an example animation of the convolution operation. We have input channel in blue on the bottom, and a 3x3 filter shaded on the bottom, and output channel in green. And the filter is sliding across the input channel to generate values for the output channel. Let's take a look at this example with some numbers. Suppose we have a 3x3 block here in green, and we have another 3x3 filter filled with some numbers. For example, negative ones on the first column. And the math operation here is to get the dot product of this 3x3 block with the filter. And the output value, the value will be stored in the output channel. The convolutional operation is going to do this step for every 3x3 block and save the generated values in the output channel. So the question here is, what does such kind of convolutional operation do, and how does it detect patterns? I have a very simple example here. This is a handwritten digit 7, and we want the CNN model tells what digit it is. And here in the first layer, we have 4 different filters, and those filters can be visualized by having negative ones in black, ones in white, and zeros in gray. And those are the generated output. In the output, we can interpret the brightest pixel as the pixels detected by the filter. So it's not hard to find the first filter can detect the top horizontal edges. The second one detects the left vertical edge, and the third one detects bottom horizontal edges, and the last one detected the right vertical edges. So those filters are very basic filters. There are some, we can call those filters as edge detectors. And there are some other filters that can detect other patterns, such as circles, corners, angles. And if we have more layers in our neural network, we can detect more sophisticated objects like the ones showing here. And as we go further into the layers, we can detect some more complicated objects such as the dog faces and bird legs here. And the amazing thing of convolutional neural network is we don't need to design those filters manually. the neural network can start with some random values for the filter and will change and modify those values through a process of training. Hope the previous slides can give you a general idea about how a CNN model detect patterns. And next, we are going to move to a case study. As you can see here, we have 8 classes of beans images captured by a color camera, including Aduki beans, brown beans, kidney beans, etc. And to make this task more challenging, we binarized the color images, which means we are not going to use the color information for the classification task. We only use the morphological traits related to the size and shape, such as the length, width, and area of the beans. Before I talk about how do we build a CNN model for this classification task, I want to mention what do we usually do if we are going to use a traditional machine learning model such as SVM. Well, the common practice for machine learning is to manually extract some morphological traits related to the size and the shape, such as the area, perimeter, the length of the axis, solidity, aspect ratio, etc. And those features can reduce the complexity of the original data and also makes those patterns more visible for the machine learning models. But for deep learning or CNN model, it works in a very different way. So instead of using those handcrafted features, a CNN model can learn those features automatically through the process of training. And with deeper layers, it can learn some high-level features that some global features cannot capture or cannot describe. For example, I have 2 kinds of beans here, the chick bean and the green bean. You may find that they might have very similar values regarding the size and shape, for example, the area and perimeter. So it might be difficult for a traditional machine learning classifier to separate those 2 classes of beans. But for a CNN model, if you look at the intermediate results here generated by a CNN model, you can find it detects some local features. For example, the curvature here is very different from that green bean has. So this local feature can make the chick bean distinguishable from the green bean because green bean has a very round shape. It doesn't have this kind of beak-like shape. The other thing I want to mention here is there are some also some disadvantages of CNN over traditional machine learning. For example, it requires a large amount of data with manually labels to achieve the high performance, high accuracy, and also requires some high performance GPUs for the computation, and also takes longer time for training. So it's kind of trade-off when you are thinking about what you are going to use traditional machine learning or CNN for your study. Now let's move to our code. I think if most of you have received a zip file which contains the data and the source code. Let's see what we have in this zip file. There are 3 items, the data, which contains some images. I show the directory structure here. There are some images in this data folder, and inside the images, there are two folders, train and test. In each folder, there are 8 subfolders for the 8 classes of beans, and I have 34 images for training and 16 images for testing. The ratio is about 7:3, which is commonly used in machine learning or deep learning process. And next, I'm going to show you how to run the code and also have a brief introduction about the code. I will start from very beginning if you want to follow me step by step. At first, we will use this Google Colab, which is a platform that allow us to execute code as well as give us the access to their GPU. So if you go to Google Colab and load the code, upload my code to Google Colab. Okay, the code is showing here, and in your Google Drive, there should be a folder created called Colab Notebooks. So our next step is going to load this data into our Google Drive so that the code can access and read those data, image data. It might take several minutes to load this data, but that's fine. Let's take a look at the code first. Well, I send the source code to you because I don't want you to type in those code line by line during this workshop, but I do want to have you have a general idea about how does this code work and try to interpret the output. Is there any questions so far? Cannot find my chat box. Oh. Okay, no question. Let's go ahead. I will first introduce the code here. The first two cells are about loading or importing the required libraries used for the CNN model. And to run this code, you just click the play icon on the left. Or the other way is to use the keyboard shortcuts, which is Shift and Enter. Oh, yeah. Yeah, if you use Shift and Enter, it will run the current cell and go to the next cell. And by the way, if you go to Tools and Keyboard Shortcuts, you may find some useful shortcuts. And the most commonly used is the Command, Control, and slash to comment or uncomment the current line. And the other one is Run the cell, which is Shift and Enter, which you can use for running the cell. Those two are the most frequently used ones. Okay, let's run this cell and move to the next one. And the next step is it's mounting the drive, because we just uploaded the image data to our Google Drive. We need to mount the drive to allow the code to access those image data. There are different ways to do this. I think you can also do it manually, and the code to do this is drive.mount. And if you run this code, it will ask for the permission. I will connect, login, and allow everything. Do you have this pipeline in R? Actually not. Well, because I'm using the the library Keras it's an API for Python, so I didn't implement that in R. But if you want to take a look at the code and don't want to run this code, you can go to my GitHub link. I will put my link here. Yeah, this link will bring you to my GitHub, and if you click this beans classification, then you can see the code and the intermediate results here. Hope this helps. Okay, it shows it's mounted. The next step is we want to use, because we want to use the GPU to accelerate the process of training. So to double check that, we go to Edit, Notebook Settings, and here you can select non-GPU, TPU. I think none means you are not going to use their GPU, only use CPU for training. This will be much slower. So I would suggest select GPU and click Save. Now we have our environments ready so far. Let me know if there's any questions regarding the setting for the environment. Well, I didn't see any questions in the chat box, so I will move on to the next part. So for the CNN model, we will start with preparing and loading the data, and then after that, move on to the building and training the model. Here, before loading the data, I want to introduce a very important technique called image augmentation, which is widely used in deep learning training to increase the variations of our training images. For example, here I load the image. Oh, by the way, before that, I want to first show you how to find the directory and specify the image path. Here we have mounted our drive. So on the left panel, you can find your Google Drive. In my case, it's Drive, My Drive, and Colab notebooks and data. So to find this path, and you can copy the path from here and put that path in this working directory, so that the code will know where your data is located. Once we specify this directory and the path, we can load an image from this data folder, from this folder. And here I loaded an image and assign some random operations such as horizontal and vertical flip and rotations to the original image. And in the output, you can see. Let me run this cell. The original image, the same original image, is transformed in different ways. Okay, next, let's use this image augmentation technique to load our data. Here we use one thing I want to mention here is there are some other augmentation technique you can try, you can play with, such as the share or resize. But the thing is, those operations need to be realistic. For example, if you are going to detect or classify a plant in the field, you are not supposed to use vertical flip, because the plant cannot fly in the sky. It's not the real case in our life. And here, based on the variations of our training data set, I use the flips and rotations to the beans images. And I also normalize the images, both for the training and the test data set. And the next step, let's run this still. The function flow from directory is used to load the data to the model. Here, one important parameter is training path, which you tell the function where's the images, and the training path is defined previously here, which is the path to the training and the testing images. Do the same thing for the testing, for the test data set. So we have pre-processed and loaded the data. Does anyone have any questions regarding loading the data? Okay, I think not. Let's move to build how to build the model. To build this CNN model, I'm using the Keras library, which is a Python API that has many building functions. It's easy to use to build a CNN model. Here I use sequential. If you want to know more details about those functions, you can go to the official website to see the full explanation. And here the sequential is used for initiate the model. And next I added multiple convolutional layers as well as max pooling layers. The max pooling layers I didn't mention in my slides. It's for downsampling and for preventing overfitting. Because it's gonna only reserve the max value in a certain area. For example, we specify the pore size as 2 by 2 here, which means in a 2 by 2 window, we only select the max value in that 2 by 2 window. This method can reduce some noise in some small regions and prevent the overfitting. So you may find the max pooling layer is always come together with convolutional layer. And in the last, we have another flattened layer, which is used for converting the multi-dimensional data to one-dimensional data and get connected to the output layer. And in the output layer, we have 8 units, which is corresponding to the number of classes. So if we are going to train, for example, if we only have 4 classes, we need to specify we need to change the units to 4 here. And the last line of code summary gives us an overview of the model we just built, as well as the number of the parameters, the number of the convolutional layers. Let's run this still. So our next step is training the model. Here, the code I sent you has 2 minor mistakes I would like to modify here. The first one is the file path. We need to provide the absolute path, which specify the working directory we defined here. Scroll up here, and the file name. And the other one is monitor, the value assigned to monitor. Because this code is the model checkpoint is gonna save the weights that has best performance on the test data set. So inside this function, we want to specify the path where the weights should be saved, as well as what kind of magic are we gonna use for evaluation. And in the output, you can find a clue. It shows a warning that can save best model only with validation accuracy available, skipping, which means this metric is not available because in its output it has loss, accuracy, validation loss, validation accuracy. So it should be accuracy here instead of ACC. So in this way, it will monitor the validation accuracy and save the weights with best performance to this path. Now let's train the model. Well, I specified 30 epochs here, and the first epoch always takes probably 1 or 2 minutes because it takes longer to converge from the initial state to a certain point. But after the first epoch, it will be very fast, about 2 seconds for each iteration or for each epoch. And as you can see here, the accuracy is changing. Oh, how to decide how? I saw a question in the chat box, how to decide how many convolutional layers you need to get a satisfied classification accuracy. This is a very good point, and I will have a discussion about this later. Actually, there's no such golden rule to decide how many convolutional layers and what kind of filter size and what kind of hyperparameters we are going to use for our CNN model. I would say play with some initial values and tune those parameters to find which of those can generate better performance. But also it depends on the scenario. Like for example, if you have a very simple data set, very small data set, you usually it doesn't require that many layers because you don't need that many parameters to describe your data set. Like in our case here, we only have 3 or 4 layers because we only have 8 classes and with some simple images. So those parameters are sufficient to describe the variations in our training images. But later on, we will have a practice to reduce the classes to 3 classes and reduce the number of layers to only 1 convolutional layers. You will find that it also produced a very satisfactory performance because the case is simpler and we don't need that many parameters. I think we finished the training. Let's take a look at the output here. If you scroll down, you can find the accuracy is increasing, but not all the time. For example, the accuracy here improved from 0.78 to 0.81, and since this is the highest performance so far, so the weights are saved to this path. And let's scroll down here. See the validation accuracy improved to 0.9887 and saved to this path. So our next step is load the best weights. If you're gonna train more epochs, it will achieve higher performance. Like the best accuracy I've got is about 0.97. Right now, because of the time, I just set it to 30 epochs. And our next step is to load the best weights we have saved during this training process. The code here is classifier. We defined previously here. And there's a function called load weight. And we put the path. We run this code. And we load an example image from the test data set, and prediction is it's brown bean. Well, you can play with it, like load the different classes of beans images for prediction. And the last 3 sections is about a visualization of the overall performance and the accuracy over time and the loss over time. I won't go to details about them. Thank you. Any questions so far? If not, we will move to some practices. Play with the code. Okay, I have 2 very simple questions here. The first is, how do we modify the network to work for 3 classes? Think about what kind of parameters we need to change in the CNN model. And the second one is related to the number of the convolutional layers. What will happen if we add or remove the convolutional layers, and how does that affect the training or testing performance? I will give you 2 minutes. If you have any idea, feel free to speak out or put that in the chat box. Okay, let's look at our solution here. I think the first step is pretty straightforward. We need to think about how we feed the data to the model. So for this function, flow from directory is going to load the data from this path, where the number of the subfolders corresponding to the number of the classes. So our first step is going to remove those image data. For example, we only reserve the first 3 classes and remove the last 5 ones. Okay. And do the same for test folder. Okay, let's try. Now it says found images belonging to 3 classes. It still says 8. Okay, it might take several seconds to make the update. Now we have 3 classes in both training and testing dataset. The next is about the neural network. As I mentioned before, in the output layer, we need to specify how many units or how many classes are there. So here we need to change this the number of units from 8 to 3 and run the model. Let's try. Oh, that's it for modifying it to fit 3 classes. And let's take a look at the next question is how do we add or remove some convolutional layers? Here I want to show you the simplest case, which means we only have one convolutional layers. So let's comment all the other layers. And this one and this one. So right now we only have one convolutional layers and one flattened layer for converting it to one-dimensional data and one output layer. Let's run this model. You can find the structure is very simple now. And let's see the performance. I think I'm running out of time. Well, the best performance here is about 0.79. Okay, that's not bad. You may find even though we reduce the many layers and many parameters, the performance is still not that bad, I would say, because we reduce the number of classes and the case is simpler. And we load the best weights, take test. Yeah. Actually, I saw can wrap up in a few minutes. Yeah, that's take a load test images here, and the prediction is still correct. I think I'm running out of the time, so you can play with adding more layers or tuning some hyperparameters like the learning rate or using different activation function, as well as different optimizer here. Okay, I will stop here. Feel free to let me know if you have any questions. Nico, I'm done with my demo.
Okay, great. Thank you so much, Derong. Apologize for running out of time here. You guys are doing some really great stuff, and obviously there's a lot of interest in this. So thanks everyone too for the great questions. Since we have run out of time, we will not be able to play Dr. Guy's presentation, but we will add that to the website. The AG2Pi website where this event is located, and we will also have a recording of today's presentations on there. So if anyone out there wants to share this with your colleagues, those recordings will be available for you there. There's also the data test set that Rong put together for everyone, which she just previewed as part of her tutorial. So again, if you did not receive my email that had that link to it, then you will also find it on our website. And with that, thank you everyone for turning up today and again asking great questions. And I guess if you have any further questions, just feel free to reach out to one of us. Anything anyone else wants to add? All right, I will stop recording.
Thank you guys so much. That was awesome.
It took too long.
You only take too long if the material you're presenting is good. But the hands-on workshop was great. I hope people get a chance both to leverage the notebook that you made and play with the sample data sets and you know, specifically put in their own. Because like I assume you can use a similar model to retrain for other shape-based discriminators that you want to make.
Yeah, exactly. This is a very commonly used CNN model, and you can use it for training other images by very few modifications.
Yeah, and if you wanted to keep the color in there as a discriminator, you can just remove that first layer where you're converting it to black and white. Is that correct? Pretty much. Yeah. So for all the plant biologists on here, who's going to develop one for counting corn kernels? You can basically do the same thing pretty quickly.
Yeah.
Or pollen. I know a lot of people ask us about pollen counts or pollen discriminators. But in any case, that was excellent. And I just have to say, between the engineering and the downstream analytics with machine learning, you have a ton of fun. And you have a field that doesn't get to 120 degrees Fahrenheit in the summer. So you definitely are a little nicer than what happens in Arizona.
We're lucky in that way.
Do you make everyone in your group go out to the field and help?
Yeah, we work pretty hard in the field, and the robot is not easy to come with.
I work a lot with Duke Polite here with his big gantry out in Maricopa, and so I've gone out there on occasion when they need help for usually weeding the field. What are some of the other ones? Oh, leaf punches, stuff like that. So it gives me a deep appreciation for an air-conditioned, climate-controlled environment to sit in and work on the computer.
Yeah.
All right. Well, thank you all. That was fantastic.
Yeah.
I'm going to sign off.
Thank you.
Thank you. Thank everybody.
Yep. Thank you. Take care.